Problem number 34, continuing on with problems in chapter 16. Now, as you're working these problems, don't just work blindly through the problem and get to the end and go on to the next problem. Be sure you understand why you are taking time to understand and answer this problem. Because in problem number 34, what you're really looking at is what are the ways that you can look at any process and make a determination about the sign of delta S. And in all of these problems, in 34, 34A, B, and C, and D, you're looking at the question, what is the sign of the change in entropy of the, is this system or surroundings? Well, it doesn't say here, and so that means it has to be for the system. Now, this system is in part A. Here you're going from 1 1/2 moles of reactants to 1 mole of products. And as you do this, you're making the system more organized. In other words, there is a decrease in the level of disorder because you're putting particles that were separated more closely together and more organized. And so the change in entropy of this system is negative. Delta S naught is negative. B. In B, you're going from 4 moles of reactants to 2 moles of products. So once again, the change in entropy of the system is less than 0, a negative value, because you're making it more compact. Here, it's not a matter of the moles changing, although I guess you could look at it as saying we're going from 1 mole to 2 moles. But you could look at this as saying we're going from a crystal structure of sodium chloride, a very organized structure, as a solid, to something dissolved in water where the particles are floating around and they're free to move. They're no longer organized. So the entropy of this system has really increased. Not only have we spread these apart, but we've spread them out. And so the delta S of this system is greater than 0, a positive number. And of course here, anytime you have a phase change, it's going to be a big clue to you of whether you're increasing or decreasing the entropy. Because remember, the solid phase is always more orderly than the liquid phase. And so we're going more disorderly here, so the change in entropy is going to be a positive number. Let's move on to number 35, which asks you kind of a similar problem or similar question, but it's just comparing 2 different phases or forms of the same chemical. And to answer here between carbon and graphite, which has the greater value of delta S? Now let's remember that question because I'm going to hide that here. Which has the greater value of delta S, graphite or diamond? In other words, which one is the most disorderly? Well, it turns out the answer is graphite, and to understand why that's the answer, you really need to know something about the crystal structures of diamond and graphite. So let's look at these pictures. Here we see graphite, and I think you're going to look at that. I'm afraid you're going to look at that and say, that stuff really looks organized. Look at all that organization. Well, that may be a little bit misleading because really these individual units that I'm drawing boxes around, those are layers that are not attached by any chemical bonds. It says there's a weak force attaching them, but those are not chemical bonds. Those are bonds that we'll call van der Waals forces or London forces that we'll look at in another chapter. So those particles can easily slough off. That's why graphite makes excellent lubricant, is because those layers can slide over the top of each other, or they slide off of your pencil. Since your pencil is made out of graphite, they slide right off the tip of your pencil and stick to the paper. Diamond, on the other hand, you'll notice the way they have it drawn here may not truly show how organized the crystal structure is, but it does show that it's organized in 3 dimensions. Very tough, very orderly. So diamond has a more ordered structure than graphite, so graphite has the greatest entropy. Now here, of course, the one with the greatest entropy is going to be the one that's in the gas phase. So that's why 35b, we're looking at the gaseous phase being more disordered than the liquid state. And the kind of the same thing down here, we're just looking to see which state has the greatest level of disorder. And so, of course, you put C for that. Moving on to number 36, which substance has the greater value for delta S? I must have left the delta out when I was typing that. I'm sure there's one there. For each pair, which substance has the greater value of S? Okay, so yes, the greater value of entropy. So how would you know 36A? Well, the key is really the temperature here. The key is really the temperature and the fact that you remember the definition of entropy. That entropy at 0 Kelvin is 0. So anything that's higher than 0 Kelvin is going to have a higher entropy than this. So helium at 10 degrees Kelvin has to be the correct answer here to 36A. In B, the key here is what's different between these? Different between N2O and helium. Well, the difference here between N2O and helium is one of them is a more complex system. And so the more complicated molecule is going to have the greater level of entropy. And so B is the answer here in 36B. And in 36C, what's the difference here that we're looking at? We're at 0 degrees Celsius in both cases, and someone asks, I can just hear you out there saying, what? How can you have solid water and liquid water at the same temperature? Well, if you have ice floating in water, the temperature of both the ice and the water are 0 degrees Celsius. Because it's going through a phase change. So that's what we're talking about here. But of the sample, the solid or the liquid, which one has the greater entropy? And of course, you know that the liquid is much more disorganized and the particles can move with respect to each other. So the liquid will have the greater entropy.